Hey everyone, good morning. My name is Dean Macris, and today for HackTheSea demo, I'm going to talk about a project I've been working on with my co-presenter, James Campbell, who's not clearly here right now, called OpenBridge. This was also presented at DEF CON Demo Labs, and we're doing it now, recorded for HackTheSea, because I somehow managed to screw that up. My name's Dean. I'm a instructor at the U.S. Coast Guard Academy, and I guess in summary, I've spent a lot of time on boats. Small boats. This is an engine room I was tearing apart on an older Hatteras. Big boats. That was a time I went to Antarctica on the Paul Buck, along with down here in the lower right is inside the boiler of the USNS Algol. Sailboats, I think we know what that is, the Eagle. Pump out boats, these were small boats that I had been working with a nonprofit that emptied the holding tanks for environmental purposes out of recreational boats, and then deposited that cargo, as it were, into the appropriate waste treatment facilities. You can kind of see we built boats, and they were kind of custom for the purpose. And we'll talk a little bit more about that, but notably we wanted to kind of increase the accessibility to the boat, make it more available for individuals to do the right thing. We figured that if it was easy to do the right thing, so one of our main tenets was utilize technology in that. We'll talk a little bit about that and how that relates to NMEA 2000. Also worked on large, pump out boats. A sledge tanker here from New York City Department of Environmental Protection, a commercial mariner, so I sailed as an engineer on these ships for almost 8 years. I think it was about 7 years, a little more than 7 years. So this is the Red Hook in dry dock in the Brooklyn Navy Yard, and I was able to kind of put that into operation and sailed on it after that. So in doing that, I really got a chance to, in the process of kind of, shaking down the boat and learning it, we got to see a lot of the sausage and how it was made in the kind of bringing all these marine systems together. So, I mean, that's a lot of industrial control type stuff, Modbus and such, but also kind of gets into the NMEA 2000 world. So that was in kind of 2008, and that was a little bit of an introduction to kind of maritime technology, maritime electronics. So kind of to follow up with that, in 2014, the boat that we were talking about, that aluminum one, we used a pretty early Raspberry Pi. I mean, I don't know where they were in 2014. They'd definitely come out, but I don't know if it was a Pi 1 or Pi 2. We had hooked up to a 3G gateway as well as a Maritron NMEA 2000 gateway, and with the help of one of my friends, Victor, we were able to essentially parse the data from the NMEA bus over the Maritron, which was a USB gateway, and then make the boat talk. When I say talk, it would tweet when it went into a marina, which we defined as polygons, geographic polygons where the marina area was. And we also figured it was probably, if you're a boat, that you'd want to tweet Moby Dick quotes. So you can still go and look at CES Big Al, and you can kind of see that in action. As you can tell, it was a huge hit. And 8 people followed Big Al, but I think it was more of a proof of concept. Pretty soon after that, we actually lost our grant funding to be bringing kind of this service to boaters. So kind of I sadly had to move on in my life to a career in cybersecurity. So, okay. In this process, I found it really difficult to get a handle as a marine engineer. So that was my trade. I'm a knuckle-dragging marine engineer. So everything I'm talking about is from the perspective of someone that went to school to study thermodynamics and mechanical engineering with electrical engineering sprinkled in there, and some naval architecture. They call that kind of marine engineering. And I found that, protocols that we'll talk about like later, NMEA 183, was kind of a serial protocol in plain text, so it was pretty easy to figure out what was going on there. And then when I moved to kind of looking at some of the marine electronics that we're talking over NMEA 2000, I had a hard time. And that's kind of what I'm going to talk about today, is how do we get started, and then how does OpenBridge kind of fit into that, and how do we kind of make this a little bit easier for people to break into, so that hopefully more people can study it, understand it, so on and so forth. So kind of after that, I got a position at the United States Coast Guard Academy as an instructor. I'm instructor of cyber systems there, so I teach a class called Computer and Network Security, which is right now first class level course. So that means for seniors, on kind of learning about kind of the operational aspects of networks, building networks, testing them, and then ultimately learning about vulnerabilities and testing those as well. And I've been lucky enough to have a capstone group that we affectionately call Hackboat. And what the purpose of that capstone group is to kind of start the ball rolling and creating kind of a maritime aspect of security in the electrical engineering and cyber systems section. So right now, last year, my capstone group was able to design, create, and implement, and this was a huge task because it was like physical design, it was organizing the electronics, hooking everything up, and then also working with the HackTheSea, which is a gateway between your computer and, I think it's an NG, I have one here, an NGT1. And it pretty much connects to a NMEA backbone and your computer. There's an SDK that allowed them to write some C# maybe code to be able to read and write information from this bus, and they also built kind of this, I guess it's that way, all the way over on the other side there. This like piano looking enclosure that served as kind of this console that students could come up to and learn about not only marine electronics, but really kind of more of a deep dive into the protocol. If you're at DEF CON 29, then think of it as kind of if you were to build your own Fathom 5 unit on a budget at home. But they did a great job, and it was like an overwhelming success, and that kind of really started the ball rolling as to like, I wanted to do this for my entire industrial controls class I was developing. So the problem was it's like really expensive. You can see some of these kind of like radar head units and GPS head units and such combined with thousands of dollars. And everyone couldn't have their own, and having one station that everyone shared was kind of not the way I wanted to approach that solution, right? Like I wanted to have everyone be able to have their own little lab kit and then utilize the full console as like, okay, you've practiced on your own, now you can go, game day on the main unit. So in June this year, so it's early August, so a month and a half ago, we kind of started thinking about putting this together into a project that we call OpenBridge. And we wanted to make hacking NMEA 2000 and learning about marine electronics a little bit easier, more accessible, more inclusive for people that didn't have a background in electrical engineering, in computer science, in even making and hacking. Like I thought of circa 2001 Dean Macris, where I was kind of very much, it was pure magic. And I think of the kind of like all of the time and money and expense that kind of got me to even just be able to have a coherent conversation about this. And I want to save people a little bit of that trouble, hopefully, and then utilize the community. Like this project is literally very much based on work that's already been done in the community. So we would never be able to accomplish anywhere close to this if we had started from scratch. So I think it's very important to point that out. I want to be able to provide kind of, if not a curriculum at this point, some self-study material where I took a lot of the resources for the NMEA 2000 protocol, and I'm saying it in two different ways, I'm sorry. NMEA is probably how it's actually pronounced, but I've just been calling it NMEA so long. So they are the same thing. If I say NMEA or NMEA, I'm referring to the National Marine Electronics Association. But it's a lot of the information is all over the place. A lot of the documents that we are essentially talking about are closed, proprietary, pay for usage, and then not be able to essentially disclose that for the obvious purpose of other people would need to do the same. So the community has really gone through and provided kind of some open source documentation through reverse engineering. There's also a lot of resources that NMEA provides that also help kind of put some of these pieces together. So I've referenced a lot of those. So everything we're talking about is kind of from that open perspective of things that have been reverse engineered. And hopefully OpenBridge will enable more people to be able to tinker and play with some of these devices, hack around to provide a little bit better insight into how some of this stuff works. So I also wanted kind of that last piece, self-serving piece, is I want to scale so that groups could have their own little OpenBridge simulator and be able to hack with that in a way that kind of gets you from 0 to 60, starting out with analyzing the protocol, learning some of the tools, and then learning how to interface with an actual backbone. That would kind of be when you plug into the the larger simulators. If you have the opportunity to go to the CTF, like the SEATF, which is the Fathom 5 simulator, this would kind of be a starting point where you could explore there. So I had some specific goals in this, and my co-presenter James has helped me kind of achieve those. So we wanted to keep the cost less than $50. We wanted to standardize the hardware and the software to get people hacking quickly. Again, from that perspective of myself being a knuckle-dragging marine engineer, not an electrical engineer, the plethora of options of how you could configure and set up some of these libraries was daunting. For someone that has used an Arduino and then tried to implement the same code on an Arduino somewhat unsuccessfully, I thought it would be a good starting point to standardize hardware. Additionally, it took a little bit of document reading, and again, read the manual, but to get kind of the software really up and working. And there's a couple of gotchas that we had found in the middle that hopefully by standardizing some of the hardware and software will get people going quickly. We wanted to keep everything open source, so the repository, OpenBridge, which is on the title screen, is the place to find that. And hopefully feel free to fork and submit a PR, and we'll get that merged into the code base as quickly as possible. It's again very young, like we spoke about. We wanted to provide some more in-depth documentation with links as to where that documentation came from, so we have kind of a robust links section, and then also some pretty verbose documentation explaining some of these topics. And then we wanted to provide the platform to be able to expand and build more capable systems. So we didn't want to really kind of work ourselves into a corner, so we can kind of talk about how we did that. So before I talk specifically about OpenBridge, I wanted to kind of talk about why this is difficult, the perspective of kind of what it is. So we'll talk about NMEA 2000, we'll talk about why it's difficult, and then we'll dig into how we can kind of crack that nut so we can get a little bit of confidence in working with CAN, working with the ISO standard that CAN is supporting, and then working with the NMEA 2000 protocol, which sits on top of the ISO. So if you think the CAN is kind of like your layer 1 and layer 2, it deals with your physical aspects, your a little bit of the data link aspects, and then from there kind of there's a little bit of overlap where you can think of the ISO standard as your kind of transport layer, and then it can serve as kind of an application layer, and then NMEA 2000 is kind of the application implementation on top of that, so that kind of takes your top level of the ISO stack. But Just to kind of take a little bit of a step back, this acronym I'm referring to, NMEA, or NEMA as I sometimes say, stands for the National Marine Electronics Association. They make marine electronics standards in the United States. They are most famous for the IMO recognized NMEA 1830-183. Dr. Gary Kessler has some great talks on that, whether it's from DEF CON last year or he had done a couple talks this year for HackTheSea at DEF CON. So you can find those. He is kind of my go-to expert on that. And he's also publishing some information papers on NMEA 2000 and CAN and the vulnerabilities associated with that. So again, he's a great part of the community and has been a great mentor to me. So thank him for all the work he's done. NMEA 2000 is based on the Controller Area Network Protocol, and it uses, as I kind of spoke about, the ISO 11783 standard for off-road applications, right? That is kind of compared to the SAE J1939, which is the automotive standard. Now, what's important to kind of realize is that both of these kind of play nicely together on the same bus, and in theory, you could have a NMEA 2000 bus that connects into a automotive bus. But the ISO standard is applicable for essentially forestry equipment, vessels, which is the NMEA 2000 branch of it, and other applications. They have separate kind of implementations for production facilities based on CAN, and CAN is, again, kind of everything sits on top of CAN, so you follow the CAN rules, and then once you follow the CAN rules, you can follow the ISO rules, and then you can have your NMEA 2000, which is kind of your parameter group numbers, PGNs. And once you know what a PGN is, you kind of can start really digging into what's in the data of that. So the PGN is like kind of what you're looking at. So in our case, our example, we're going to use wind data. So there's a PGN that says, hey, if you're going to put wind data on this bus, then it needs to look like this, right? And I'll go through how we figure out what a PGN is, because it's not entirely obvious. And then we'll actually take a look at some information on the bus, and then we'll kind of see how OpenBridge can make it easier to study this and play with it without the need of a real wind meter. So hopefully this will come together, because you know how demos are. Okay, so in a NMEA 2000 backbone bus type scenario, this is normally what a system would look like, right? And we have in this like drawing here, we have a chart plotter over on, I guess it's your right, possibly my left, above me. You have that connected to this backbone, which is along the bottom, and you have that powered 12 volts, so that kind of like power over Ethernet, the devices have like power that they can utilize to power themselves. You have a small instrument kind of display unit, which actually in our demo unit we have as well, and a couple sensors. And then the backbone has an extender, so you can put a piece of the backbone on the bow and a piece of the backbone on the stern. So that's kind of what a standard bus will look like. This is the lighting, and my webcam is not happy. So in order to be able to see the display here, I had to have like kind of the lighting very low. But right here you can see a little bit the backbone that I have in my lab environment here. Above it, ooh, geez. Here we go. Yep. This is going perfectly. I have the OpenBridge kind of perf board here with kind of my hardware ready to put information on the bus, and I can hopefully do a zoom in on that. And then above it is a Garmin multifunction display, really not digging into that. And if you were to see slightly off screen, I have a wind sensor. So right now that's kind of the system that we're looking at as far as the demo goes. So I kind of wonder why. Oh goodness, hold on. Let me move, because I'm kind of killing the chat box here. I often wonder why this is difficult to get. I mean, I don't wonder why it was difficult for me to get, but I sit here and I'm like, why? A lot of people that are developing this stuff, it's easy for them, right? Or they spend a lot of time, or both, right? Like they enjoy it. So again, we sit on the shoulders of giants. But when I learned about electrical systems, it was kind of basic, right? You had some sort of thing that you're controlling on a wire, and you had some sort of thing that's controlling it, right? A switch and a light is a good example of kind of a single wire controlling a single device, right? One signal on a single, on a single line. This kind of extends to, reading a signal. In this case, it's a fuel sensor, like a potentiometer, that varies resistance with the height of fuel or whatever's in the tank, and then can essentially convert that into some sort of signal, analog signal with magnetism on a gauge of some sort, right? And there's lots of iterations of this. When I talked to one of my chief engineers about what I was doing, it kind of resonated in what I would expect the normal kind of reaction to a marine engineer really doing a deep dive into NMEA 2000. And as you saw, he said the only thing you really have to know about that stuff is restart it, and if it doesn't work, start it on fire, right? And this is the same engineer that had always said, we have to move the ship, right? So if I'm fiddling around with something, or kind of like building something from scratch, or really kind of like digging too deep into something, he'd be like, Dean, you're building the clock to tell the time. Let's just tell the time, right? And for most applications, that's super important to get stuff done. In this case, we're going to do a little bit of a deep dive into building of that clock. But I think it's just important to note that kind of, we got here because there's so much tech that goes into boats. So like people that are operating them really have a hard time getting a handle on it. Another reason, is that we just a lot of times don't have the right tools. So this is an example of how we go from a single signal on one wire to multiple signals on a wire, right? So we have, in this case, two wires, a CAN high and CAN low, but you can, I'll show you, you can use just one of them. The second wire kind of gives you a more robust, signal because your differential voltage is pulling high and low. But now you've got three nodes on a bus, so you got to sort out which is which, right? And that's what the control area network does for you. The issue that we have is that, and I'm sorry, I've got like my TV over here, so like very often I'll be like, what's over there? We have the wrong tools for that, right? As a marine engineer, this is kind of our tool of choice, and then we get a lot of these analyzers, these widgets that we get given that can, read and translate the bus, but we don't really know what's going on. And as I found out, like, sometimes these tools by default don't give you all the information that's on the bus. So, for instance, you plug in the yacht devices, I have one somewhere here, the yacht devices analyzer, here it is. And that will show you all the NMEA data on the bus, but it doesn't show you kind of the ISO, like network level specific information that's going on. So it won't show you the ISO requests, it won't show you the replies, it won't show you a lot of what's going on with errors and such. So it really kind of ties your hands. So we have to get kind of the right tools, and in that we're saying the right tool for part of this, the exploration. Part of it will be finding some sort of logic analyzer. The one that I've found that I enjoy using is made by Salier. As you can see, their software kind of here is absolutely beautiful, super easy to use a lot of capability that these devices have in a very beautiful format for someone that's not doing this every day. It's something that's kind of designed for us. And here we go again, right? We're going to need to move my video over back to where it was. Okay, so the kind of nice thing that Salier does is they have enthusiast pricing, so they kind of have a hacker mode where if you're not using this in a professional sense, I think you probably agree to say I'm not using it in a professional sense, and you get their Logic 8 for half off, so $399 device for $199. You can use analog discovery, which is similar. Software is it's a full oscilloscope, so it's got a lot more functionality, but it's also a little bit harder to get going on. And then you can also find various different logic analyzers online, depending on kind of like what your price range is. So it's really, you kind of pick what you want, and you'll find something. So now that we kind of know how we can look at this information, let's dig in and look at how we would decode this, make a little bit of NMEA traffic, and we can talk about OpenBridge. So right here with me, I have, and this would, if it's an in-person demo, you'd be able to see it. This is kind of a deconstructed NMEA 2000 drop cable. And as you can see, it's got shielding. Shielding is grounded to the system at one point, right? It's kind of like a bonding wire. You have your 12 volt plus, you have your ground, right, as a red and a black wire. Those are fused at the power point, if you noted that. And you have a CAN high and a CAN low. In this case, the CAN high is white and the CAN low is blue, right? So if you follow the OpenBridge bill of materials, you can essentially pull one of these apart and use this to start connecting your OpenBridge to networks. When you actually start like plugging into these wires, you're going to see that there's kind of two states that the bus can be at. It's a recessive state where the voltages on the CAN high and the CAN low are the same, and there's a dominant state where on the CAN high you get pulled up in voltage, and the CAN low you get pulled down in voltage. And you can see how that gets a pretty aggressive bit that's shown by having one bus pull up and the other pull down. We also in OpenBridge utilize a transceiver, and what that does is it essentially takes CAN high and CAN low and it turns it into a CAN transmit and a CAN receive. So it can interface with devices like the TNC. So all that's doing is essentially, imagine if you look at kind of that sawtooth signal there, that if you just took out the CAN high and followed the CAN low, it's very similar to that. Instead of focusing and sitting around 2.5 volts and I think it's like 1.3 volts, it goes between, in this case, 0 and 3 volts or 0 and 5 volts, right? To create a clean signal, and we'll see that when we actually look at the data. So if I go to the next screen here, and I use, with the having myself in the wrong spot again, move myself back over. If we take through two channels here, so channel 0 and channel 1 in this case are looking at CAN high and CAN low, and we can kind of see that there's this 2 volt signal here. So we're sitting around 2.2 volts, and when we get a bit, we pull down to a little bit below 1.5 volts, right? And when that bit's over, it kind of returns to its recessive state at about 2.2 volts. You can see that on the flip side, on the CAN high, we're sitting around 2.2 volts again. It's kind of a little bit off screen here, but it'll pull itself up to about 3 point something volts, 3.3, and then it'll pull itself back down to that 2.2 volts. So we're, imagine it's one is pulling up while the other is pulling down. Channel 3 is actually on the receiving side of the transceiver. So the receiving side of the transceiver is looking what's on the bus, and it's reading it, and the receiving side of the transceiver is correcting that to between 0 and 3.3 volts in this case. If we take it one step further and we add on a channel 3 with a digital overlay on it, you can see how it cleans up the channel 3 on the bottom here and gives you kind of this nice visualization of what the data should look like, right? If you're not looking at actual electrical signals, the data should look like this, and we can start seeing what's making bits. You can see that also with the CAN analyzer using Salier on, and I could probably make a separate video on just kind of getting started on the Salier logic analyzer, but I mean there's people that probably did that as well. You can see that it first looks at each section, and it can look at the different parts of the CAN protocol and break it up. And right here it's identifying an extended identifier. You can see that it's also showing you 8 bits. There's kind of this control block here, which tells you how long the number of bits are, and then it counts 8 bytes. I'm sorry. So this is saying, hey, there's 8 bytes coming, and you see 1, 2, 3, 4, 5, 6, 7, 8, and there's kind of a checksum, a CRC checksum here at the end. So that enables every node to know that what was sent is what was intended to be sent. So we've pretty much gone from voltage on a wire to now something that we can kind of start digging into to break up. We still don't know what this is, right? It's a frame, it's a CAN frame. We don't know if it's a NMEA CAN frame or whatnot. We know it's extended. The identifier is 29 bits, so it's an extended identifier. So if we go to the next screen here, I think I was incorrect there. The last one was a regular identifier, which was 11 bits. This is an extended identifier, which is 29 bits. So when we look at the extended identifier, I made this little kind of drawing, and this is in the, look at me. Let me just get rid of, you guys don't need to see me, right? I'll just get rid of myself. There we go. That's better. So if we zoom into just the identifier, we can start breaking up the different parts of the identifier. And pretty much from this RTR bit here to the starter frame bit at the beginning, you can see that there's I denoted these different colors. And I'm not going to dig into exactly what each section of the CAN identifier means and all the detail, because it's extensive, it's very specific in how you can use it. I'm just going to kind of show how we can take this identifier and turn it into a CAN, a NMEA 2000 parameter group number. And again, there's not really any magic here. It's just kind of knowing the formula, right, to be able to make the sauce, right? So what we did as we zoomed in, you can see that Salier specifically put in a lot of these little dots, and that denotes bits. You also notice that some of the dots are not dots, but they're X's, and that is essentially how CAN synchronizes. It uses like leading edges and trailing edges to synchronize its timing. I think it's mainly leading edges. So every 5 bits within kind of the normal frame, not in the checksum, I believe, it will, every 5th bit of a certain type, if it's 5 recessive bits, like this first example showing, it will give you a dominant bit. If it's 5 dominant bits, like this section is showing, it'll give you a recessive bit. And what that does is allows all of the nodes to kind of synchronize on each other. It can go, they found, it can go a certain number of bits before it starts moving out of synchronization, and then it needs another bit to throw in there. So the CAN controller itself, not the transceiver, but the controller, will usually filter those out. But the logic analyzer will show you them, which is kind of nice. You can kind of see that the first dominant bit is a starter frame bit. In this case, dominant bits are 0. And keep in mind, like that's why we kind of started from the beginning, is that everything's on the node. Every node is listening, and every node, I mean, it could transmit, right? So when you're listening on the wire, you hear the first starter frame bit, you see the first dominant bit come down the wire, and then you start listening, right? If in the event that you are transmitting at the exact time that the starter frame bit from another node comes in, you don't know who has the priority. So you go into a process of arbitration. Again, a little bit beyond kind of the discussion today. We can maybe do another video on that too. I'm going to make myself a little series here. The next 3 bits after the starter frame bit set the priority. Again, this is ISO standard, so kind of everything inside of the blue, right? So the light blue there on this bottom section is kind of an overlay from the ISO standard. The blue stuff is kind of how CAN works. All CAN cares about is that you have the right number of bits in the identifier, and their identifiers are just like straight up arbitration, which we can again talk about. It's like which one has the first recessive bit. So every, it can either be a 0 or 1. If you are a 0, then and the other node is a 0, then you go to the next bit because what you're transmitting is the same. Eventually one node A, let's say, will have a recessive bit, when node B will have a dominant bit, and then the node with the dominant bit will win out, and the one with the recessive bit will become a listener to try to retransmit at a later time. So very brief arbitration discussion, and that's kind of how CAN avoids collisions and talking over each other, right? If someone's talking, you're listening, and if you both start talking at the same time, the minute that someone finds out that they are a lower priority of one way, shape, or form, and in this case, lower priorities are more dominant bits, right? The lower the better. You can then see after that you have a reserved bit and a data page bit. Those will come in handy later when we calculate the parameter group number. You have the PDU format field, which is separated by 2 bits that essentially identify this as an extended extended identifier. So if they were set to 0, they would essentially say, hey, we're done with the identifier. In this case, they're set to 1, and this is an oversimplification, but it says, hey, there's going to be some more traffic telling us about the identifier. You can see the PDU format field is kind of broken up between those two. So luckily, the CAN filter here for Salier provides you with removal of those items. The next section here is the PDU specific field. It can be used for a lot of different stuff. I think that in the standard for ISO, they call this use of the PDU specific field the group identifier. But for now, just say, okay, 0000010 is equivalent to a decimal of 2, and we can kind of move on. And lastly is where the node is coming from. In this case, it's node 23, and that was something that we actually, this is a frame that came from OpenBridge, and we pre-programmed that in. So at the end, you can see kind of these are the bits that say, hey, the identifier is over, and then the next section says expect 8 bytes of data coming after. So what we really need to hone in on here is to calculate the PGN, we have to take the reserve bit, the data page bit, the PDU format field, and the PDU specific field, and we have to use them in this kind of, if you didn't know about it, now you know, calculation. So there's kind of two scenarios, and my typo, I think, has propagated. This is just greater than 240, and the scenario 2 is less than or equal to 240. But that being aside, essentially 240 is the magic number. If the PDU format field is over 240, you set the last 8 bits of the PGN, when you're calculating the PGN, to 0, right? If you didn't know that, you're like, oh, great, now I know, right? And you take the reserve bit, like I said, and the data page bit, and you kind of smash them all together. As we're kind of showing in this little, horribly written diagram here. We have a reserve bit, a data page bit, a PDU format field, and then 8 zeros when we are greater than 240. In this case, we are greater than 240, so we take our reserve bit, which is 0, bloop. We take our data page bit, which is 1, bloop. We take our PDU format field 1s and 0s. We're taking out the SRS bit and the IDE bit, and we put those in. In this case, it's 1111101, right? And then we do nothing with the PDU specific bit, right? And when we put that all together, we get a decimal. So that's the binary when it all goes together, right? We get a decimal of 130,306, right? The correlating to wind data. Scenario 2 is when we are less than or equal to, I'll fix that on the slide, but less than or equal to 240. And again, in a similar fashion, reserve, data page bit, PDU format field, right? In this case, it's a different frame, and it's 240. And we have now replacing the 8 bits at the end with the PDU specific field, which is equivalent to a, oh wow, I didn't update the number there. Ooh, gosh. Again, another little snafu there. I'll fix that, but it really doesn't matter. The slide is not as important because the diagram isn't as important. You get the idea, because when you put all the decimal together, all the binary together, you get a decimal of 126992, which essentially correlates to the PGM system time. So hopefully that is, like if you didn't know this, it would be very difficult. If you knew it, then it's pretty simple, right? So if you're wondering, like, how did you get the PGN, right? Like, how did I know it was wind? How did I know it was time, right? I took this number now that we came up with and turned it into something, right? Wait. There's a couple of ways you can do that. NMEA has a search function that you can go to, and you can put a number in here, and you can search it, and it can come back with what it is. In this case, 60928 is an ISO address, and it just gives you a little description of what it is, right? So that is one way that you can essentially find out what the PGN is. Canboat, the project, again, which a lot of this is based on, is also has a pgn.json in their analyzers directory, and you can kind of do the same thing. Here you look at 59392 is ISO acknowledgement. The nice thing about CANboat, and this is like spoiler for the next slide, is it also gives you what is in the data, right? It tells you when the start bit is, when the stop bit is, you know, the length of it, and the start, giving you kind of the offset of where it is. And each one of these will tell you, okay, well this section is reserved, and then this section is for the PGN, right? You go to the next ISO request, right? You can go see the same number. What was the number that we used? 60. Okay, so it just gives you a little bit more context into it. So if we do a Control F, oops, and we put in our 60928, you'll see ISO address claim, right? And you can go through and see that there's a manufacturer code, device instance lower, device instance upper, right? Reserved, and then it gives you kind of a very nicely broken down section as to how you would set these bits if you wanted to write on the bus, or how you decipher them if you want to read on the bus. So again, hats off to the CANboat team and everyone that's contributed there. CSS Electronics actually has this really nice spreadsheet that is in Google Docs that you can copy for yourself. Did I click on the wrong thing? Oh, no, I did. Here we go. And this is for NMEA 2000, J1939 protocols. And you can see actually just people come in here and put in their, you know, CAN ID hex, and it will just convert it for you. So if we go down, I mean, you could really overwrite someone's thing if you wanted to. We go to a field and we just paste in our number. Oh, that's a PGN though. Hold on. We want the ISO identifier for it. I wonder if it works backwards. I don't think it's going to work backwards. This is a calculated cell. If we had the, in this case, the CAN identifier, so like one step more raw, right? And let me just pull up a CAN identifier here. Okay, so this is one that we have seen on the wire. I can just paste in the hexadecimal code here. So this one's 09FD0217. It'll give you the decimal equivalent of that, you know, fancy. It also breaks up the priority bit, right? So priority is 2 in this case. Reserve bit's 0, 1, does the same thing. PDU format, things we just did manually. PDU specific, right? Source address 23. We saw where all this came from. And then it gives you 130306. So this is the WIN data. It also shows that it's included in the NMEA 2000 DBC. They sell databases that have these in them. So if you did want to buy that, you could follow that link, I guess. It's like, I think 200 bucks, 200 euro. It's a little more than 200 bucks. But again, that gets you a degree of, you know, a little bit more information. And then lastly, if you go to the OpenBridge repo, you'll see that we put together a little Python script that will essentially find your PGN. So usage of that is, you know, you would clone the repository. That would be, you know, install git clone, you know, the Dini OpenBridge, whatever it is, it's on the main page. And then you change directories into tools, and then run the Python pgn.py program, giving it a hex identifier, right? So if you put it in the hex identifier, it will tell you, okay, here's your binary, priority bit, right? Your PDU specific, your group extension, and ultimately your PGN and your WIN data. So we're getting these PGNs directly from the NMEA 2000 website. Where is that? Somewhere here. Can't see it on my screen. So that's where that lives. So that should be able to provide you with kind of at least the ability to understand what you're looking at, right? And hopefully that kind of takes a curtain away from how some of this stuff works, because now you can actually see, you know, you have the tool to see what you're actually doing there. So we show that we can decode PGN with a logic analyzer, and there's various data fields for every PGN, like we saw. And then in CANboat, the PGN's JSON is a way that you can kind of change that. In that contextual data fields, you can see some of those things are scaled. Some of them are, it'll identify the units that they're in, and that should be able to allow you to one-off be able to decode things if you just have one frame. Or if you have multiple frames, you should be able to essentially decode that in any way that you like. So just kind of up to you how you want to skin the cat, right? Like, how do you want to go about that? The great thing about having it be, it's actually in XML and JSON, and I'm assuming they generate those when they update them, but you can then programmatically set up a way to parse through those if you want to. So again, up to what is OpenBridge, and we're pushing 45 minutes here, so I'll try to keep this under an hour. The vision is that OpenBridge will provide a standard hardware software platform that can essentially communicate from your computer and become an entire suite of electronics that you can play around with, research, and learn with, and could put onto a real NMEA backbone if you like. So imagine you have a laptop, and on the laptop you have some sort of containerized version of a wind sensor, depth sensor, GPS. Like right now we have, and you'll see how we do it, it's just Python scripts that feed in some sort of external data feed, but as it matures, we hope to kind of be able to abstract that into a container for the purpose of making it easy to package, easy to download, and kind of be able to provide additional services. If it's a display, it'd be nice to maybe build in a web server where we can see what the display would say, right? So imagine you can build this into whatever you like. But we kind of started with the hardware, and we started with a proof of concept functionality, and that's kind of what I'm going to go over. What I'm going to go over today. From there, we standardize on a TNC 4.1. TNC 4.1 has 3 CAN interfaces, so you could really, the initial board design, we have the ability to interface with 2 of those CAN interfaces, but we could build out a revision to that board that has a 3rd. I think it's something like 600 megahertz. It's pretty beefy, and it fits within our budget. It's $20-something. It's the most expensive part of OpenBridge, but it's also supported by Timo Leplino's, I'm just butchering that last name, TNC library. So again, built on the shoulders of giants. So kind of to keep with the promise of staying under $50, you can get a TNC for about $26, and you can get 5 transceivers, not 1, but 5 transceivers for $11. And if you go to our bill of materials, you can see kind of breakdown links to all those things. The board will work with a TNC 4 or TNC 4.1. For $6 more, you get the capability to have a micro SD card that can use for logging, so you can make your own CAN black box from kind of the same platform. I have some information on the CAN transceiver, the data sheet, if you want to learn what that's actually doing, from a chip level, and then there's a 5-pack for $11. I have some drop cables here, and we'll see on the next slide here kind of the next version of that. So if you want to buy a proto board, I think it's a 10-pack. I cheat a little bit. It's like 10-pack for $10, so I just said $1. But you can usually source these relatively inexpensive. You would buy a NMEA cable, kind of like this one, $15, so you could rip it apart. And then you would add on your TNC headers, and that will be about $53. So we're still in the $50 range. And then again, when we actually make a board, we're hoping that we can get it out the door with a TNC for $50. If you are interested in getting one of the first runs of the board that we're having made, please find James on Discord. He's soup7933, and we'll have like the first 50. I'll mail them out. You'll have to give them an address, sorry, or come pick it up in Connecticut. But either way, we're going to have a run of boards made, and we'll send those out so you can play with them yourselves. And again, we'll be sticking probably to that $50 range, which might mean that we have to make some concessions somewhere, but stay tuned with version 1 board. The design for the board is already on the GitHub, so you could go to JLB PCB and get some boards cut, or however, I guess people can chemically make boards, or you could use a little board mill. So it's currently a baby, right? OpenBridge, and hopefully, people that have seen this video that are interested in making, kind of NMEA 2000 exploration a little bit easier to get a handle on, can help contribute, help drive the project forward. But right now we're just kind of showing a proof of concept. With that proof of concept, it's going to be a single device that can be pre-programmed, right? That's like pretty simple. That's like what is already available. That's people that have been fiddling with NMEA 2000 wanted to make something on a bus, so you pre-program the chip to do something, and it can do that. We extended a little bit by having a CSV that you can import external data from, and we're in the process of extending that beyond, and we'll talk about that a little bit later. And we also have a multi-device example where you can essentially have more than one device. The board can support, X number of devices, and then you can feed each one data, and it can put that information on the bus. So that's kind of where we're at right now. What we've been able to do since June. I do have like a full-time job too, so it kind of has been a little bit of a passion project up to now. James has been, really carrying the weight on that. In the future, we're going to implement teensy code and abstract it from actually needing to load on what devices. Right now, you have to load up like a wind sensor, a depth sensor, whatever it is, onto the firmware when you flash the device. We're hoping to abstract that away, so you just send it pretty much the frame you want to put on the wire, and it's able to put it in the correct format for CAN and put it onto the wire. We want to be able to pull data from different feeds. For instance, give it an AIS target and pull, using an AIS API, pull like real vessel data from where it is, and you can be as elaborate as you want. My vision would be to, give it a target, have a couple containers, and each container knows kind of where it can pull data from given a certain parameter. So for instance, the GPS position will feed from AIS, and the depth of the water may not be like something, I don't think it's something in AIS, right? So you'd have to go find another resource where you could give it a position and get a realistic depth. I don't know if that exists as an API, but if it did, that would be the vision, is that you can start putting these together. Like if you had a weather API, you could give it the location where the boat is at, and you can get realistic weather information. So you could essentially make your boat simulation bridge anywhere, and make it be following a boat real time. You could also replay historic data. And then we're also working on containerizing the individual nodes. So in this case, we're just feeding it in data from our host, our computer, in the form of a CSV. You can think of that as feeding it in any format that you like, but we want to abstract that so that the device is kind of standalone, and you'd be able to just get the depth device, let's say, and it would be accepting some standard kinds of input. So that enables us to like put a web server on for the displays or a chart plotter and start essentially emulating some of the functionality of those devices. As you can imagine, it's like super complicated to really understand everything that these devices have pre-programmed, because there are even proprietary PGNs on there for configuration and management of other devices. For instance, the Meritron DSM 150 has the ability to configure remotely various aspects of different Meritron devices that are on a NMEA 2000 network. So you can imagine it will send PGNs that will change different parameters on a depth sounders, let's say. So those things are not even published in the standard. They're things that are proprietary just to NMEA and the manufacturer. So as people can reverse engineer those, and there are a number that are already in CANboat, we can learn a little bit more about how we can actually remotely configure devices, and then the world's your oyster at that point, right? You can have them be interacting with each other, and you can create some pretty crazy scenarios that can then be put onto a regular vessel to test various different things. Like kind of my other use case for the platform is that you could create devices that have certain things. Like if you want to shut down engines, if a certain condition comes in and you have a way to shut down your engines over NMEA 2000 and you have a certain way to create a condition, you could use OpenBridge to create that condition to see if your engine's shut down. So you don't have to like go to the extreme scenario to test that. So again, just an open platform to be able to do that. Before I do the demo, I just want to kind of jump in and thank my virtual co-presenter, James, and his address for Discord is up there. I want to thank Julian for designing the board, everyone that's contributed or maintains OpenBridge and CanBoat and OpenSkipper. And then, oh, here we go again with the picture, right? I want to thank Timo, who pretty much wrote and maintains the libraries that we're using. Again, built on the shoulders of giants. Most of the credit for this should go to him and the contributors to that project. The link is there. My Hackboat group, the Academy, for helping me get here and paying such. One of my mentors, Stratos, is the OG Hackboat from the late 90s. And then as the meme below me indicates, Joram was the master of all memes on the presentation, and I told him I'll leave whatever you put in, so he did. So thank you, Joram, for that. Okay, with that, let's jump into kind of what's going on with OpenBridge. So I'll zoom in a little bit here, and I guess a shout out to the Coast Guard Academy Cyber Team, Cybears. Again, have been kind of my bedrock throughout the pandemic to help me get some of this stuff done. Okay, so this was just a demonstration on the Wind Data PGN. We did that. If you go into source code and you've already flashed your TeamC, I'm not going to go over flashing the TeamC again. That'll add that to the next library. You'll see that essentially what we have is a Python directory, and within the Python directory, if you've flashed the specific code for being able to input data from a CSV, you'll then be able to essentially point to where the device is plugged in at, and then use the CSV to feed in the data. So let me just really quickly transition here to the board, and I'm going to pause and get some real wind data going. Okay, live demos, right? Things went really well yesterday. Today, I'm not sure what happened in my transporting the board home, but I think we're back to where we should be here. Okay, so last time I left off, we were looking at essentially generating some traffic on the bus with OpenBridge, and kind of show that we can give a CSV. In this case, it's sample simple CSV, and using our Python script, just send it as wind data. So I've already flashed the device with the wind input INO. That's found in the directory with, I can show you really quickly here. If we go into the repository, oh, not that OpenBridge. It's github.com/Ladini/OpenBridge. And if we go into source Arduino, we have multi-send, which is sending multiple devices. We have just a simple test wind, which is sending a single device with just preset, iteration pre-programmed into it. And then we have working wind input. Working wind input INO will get essentially, you can download that and run it in Arduino. There's instructions in OpenBridge on how to configure your Arduino to work with the TeamC. You select the port that you're on. I use a serial port. It works. And then you would be able to just flash this onto the TeamC. Once it's flashed on the TeamC, then you'll be able to, I'm looking at the screen over here, this huge screen. You'll be able to start running it. So in this case, I'm going to run sample simple CSV. And as it runs, you'll see it starts putting values on the bus. If I'm collecting data on the bus, and it's not working as it was just a moment ago. I'll be pausing for 1 second. I had to pray to the demo gods for a moment, but what's happening right now is we're seeing the OpenBridge traffic going across the bus here. So this is the logic analyzer. I ran the program, and you can see it'll flash across. So if we pause it, you can go and zoom out a little bit and pull one of the data packets apart. You could decode it the way you see fit, right? So to kind of switch over to look at the box, let's just see if I can make the color. Oh, that's a lot better. So right now the program ended, and it's in the process of, actually it's still running. And you can see that we have pretty much manipulating the bus data, and if we just switch back, we can see that, you know, it's scale factors off, but you can see that we're putting the information onto the bus and changing the pretty much the speed of the wind and the direction of the wind using a pre-filled CSV file. And you see we could pretty much set it for whatever we want. So the minute that we stop, the default condition is to leave it where it is, so it'll stick at that 45 degrees. I just control C out of that, and it'll stay at 45. And the minute that we take the node off the bus, it'll return to the regular wind setting. So I just unplugged OpenBridge, and you'll see that now I'm using the AirMar, and I'll give it a little bit of simulated wind there. You can see that now it's reading the correct wind. So again, how you extend this is kind of up to you. We're going to be working on making a little bit more documentation around it, and again, like I said, developing curriculum. But with that, thank you very much for watching the HackTheSea demo. I really look forward to engaging with the community to make kind of this platform a little bit better. And I just wanted to reiterate thanks to everyone that has worked on the project, both OpenBridge, CanBoat, and TNC, NMEA 2000 libraries, drivers, so on and so forth. The entire community has pretty much made this possible, and I've just hobbled it together. So again, don't forget to write James. You can go find the information on OpenBridge in the DEF CON Discord, and also in the Demo Labs forums. So please feel free to also reach out on the Dini on Discord as well. So thank you guys all for watching, and have a great rest of the conference.